The DC world. What if Tesla's AC system failed? The late century War of the Currents was a pivotal moment in history, a battle between Thomas Edison's direct current and Nikola Tesla's alternating current. In our timeline, AC's superior long-distance transmission capabilities led to its triumph and the modern electrical grid. But what if, at a key moment, a catastrophic failure had discredited AC, leaving the world to be built on Edison's DC? This scenario explores a world born of that failure. The Chicago Calamity, 1893. The 1893 Chicago World's Fair, or the World's Columbian Exposition, was intended to be the grand stage for AC to prove its superiority. George Westinghouse, backed by Tesla's patents, won the contract to light the entire fair. But in this timeline, a tragic flaw in a key component leads to a massive public disaster. On the night of the fair's grand opening, a transformer at the main power station catastrophically fails, causing a chain reaction that plunges the entire fair into darkness. The subsequent electrical fires cause panic and a devastating loss of life. The media, heavily influenced by Edison's relentless public relations campaign, seizes on the event. Edison's propagandic claims that AC was inherently dangerous and unstable are seemingly proven true. The incident becomes known as the Chicago Calamity. Tesla is professionally and financially ruined. His genius is dismissed as recklessness, and the promise of AC is shattered in the public's mind. The path is cleared for DC to become the sole, undisputed power standard. The Age of Localized Power, 1890s to 1940s. With AC discredited, the world's electrical infrastructure develops along Edison's model, a patchwork of small, localized power grids. Since DC can't be transmitted efficiently over long distances, every major city and industrial center is powered by dozens of small, scattered power plants. Factories are built in close proximity to rivers or coal mines to power their own operations. Urban centers are dense, with every neighborhood having its own small generating station. The iconic hum of a distant power line is a sound that never becomes part of the human experience. This has profound societal effects. Rural electrification is nearly impossible, leaving vast stretches of the countryside without power. Long-distance travel and commerce are hindered, as the electrification of railways beyond short, urban routes is not feasible. The pace of industrialization slows down, as large, centrally powered factories that would define the 20th century in our timeline simply do not exist. Innovation becomes incremental, focused on improving the efficiency of small-scale DC motors and generators rather than on revolutionary grid technologies. Technological plateau, 1950s to 1980s. The limitations of DC power create a technological plateau in the mid-20th century. The idea of a natural, let alone continental power grid is a pipe dream. The proliferation of small, inefficient power plants leads to rampant air pollution and a dependence on fossil fuels in every urban center. The development of early computers and mainframes is severely hampered. These machines require massive amounts of power, and without a reliable, high-voltage grid, they are relegated to a few isolated research facilities and large corporations that can afford their own dedicated power generation. The information age is delayed by decades. The absence of a unified grid also stifles globalization. International trade remains dominated by physical goods, as the digital economy cannot take hold. There are no worldwide communication networks, as the infrastructure to power them does not exist. The Cold War, in this timeline, is fought with a different kind of technological race, one focused on a more efficient fuel source for localized power plants and ever more compact batteries, rather than the space race. The slow unification, 1990s to the present. The world eventually realizes the severe limitations of its decentralized DC power. In the late 20th century, a breakthrough in solid-state electronics finally makes high-voltage direct current, HVDC, transmission a reality. But implementing it is a monumental task. The world's existing infrastructure is not designed for it, and the cost of building a new, unified grid is astronomical. National governments embark on massive, multi-decade infrastructure projects, tearing up streets and rebuilding power lines, to connect the disparate power plants into a single network. This is a slow, painful, and inefficient process. Today, in this alternate present, the electrical grid is still a patchwork of old, low-voltage lines and new, expensive HVDC conduits. Power is more costly and less reliable than in our timeline. The technological head start that our world had from the widespread adaptation of AC is a lost advantage. The name Nikola Tesla is barely a footnote in history, a cautionary tale of a brilliant but unhinged inventor whose most ambitious idea was a spectacular failure that cost him everything. The world is less interconnected, less uniform, and arguably less advanced because of that single, catastrophic night in Chicago. A timeline of the DC world. 1983, the Chicago Calamity. The world's Columbian Exposition's electrical system fails, leading to a catastrophic fire and a public outcry against AC power. 1901, the first power hub city is established in New York, with dozens of small, local DC generators powering a dense urban core. 1910 to 1920s, the power syndicate era. Corporations like GE and Westinghouse, which shifted its focus from AC to DC, established local power monopolies within cities, controlling small, profitable grids. 1932, the Great Urban Blackout strikes several major cities during a heat wave. The decentralized grids are unable to handle the increased load, leading to widespread power failures and rioting. 1950s, the rise of the pneumatic city. In a bid to power heavy industry without massive electrical cables, some cities begin using compressed air and water pressure for power transmission in factories. 1964, the first dedicated computer labs are established. These are isolated buildings with their own small power plants, used by the military and few corporations. The machines use a vast network of vacuum tubes and are far less efficient than their AC counterparts in our timeline. 1973. The global energy crisis hits hard. Because of the reliance of thousands of small, inefficient power plants, the world's cities are particularly vulnerable to oil price shocks. This catalyzes a renewed interest in more efficient DC technologies. 1987. The first successful high-voltage direct current, HVDC, test line is established in Japan, finally making long-distance power transmission a reality, decades after our timeline. 1990s to 2000s. The Great Grid Rebuild begins. National governments start the slow and monumental, expensive process of connecting their decentralized power systems with HVDC lines. Today, the global power grid is still a work in progress, with many regions still dependent on localized DC power. Electrical power is more of a luxury than a given, especially in developing nations and rural areas. Alternate and compensatory technologies. In a world where long-distance AC transmission is a failure, other technologies would have been pushed to the forefront to compensate. Advanced batteries. The quest for portable, reliable power would make battery technology the leading field of electrical engineering. Instead of focusing on grid-level energy storage, vast resources would be poured into creating high-density, fast-charging batteries for everything from vehicles to household appliances. We might see early versions of solid-state or flow batteries that are far more advanced than anything we had in the late 20th century. Pneumatic and hydraulic power. For heavy industry and even some city functions, the lack of an efficient electrical grid would lead to a greater reliance on compressed air and water pressure for power transmission within factories and city districts. City power hubs would feature massive compressors and pumps to deliver power to nearby factories via a network of pipes, a system that would be loud and leaky but effective. Thermoelectric and thermionic generators. With the inability to move electricity long distances, there would be a massive demand for localized power generation. Research would pour into thermoelectric generators to convert heat directly into DC power, and thermionic generators that work on a similar principle. These could power individual homes, small factories, or even vehicles, using everything from coal to nuclear isotopes as a fuel source. Decentralized communication. The information age would be delayed and would look very different. The lack of a global energy grid means no global internet. Instead, we would have small localized netlets or data compacts powered by a local grid. The transfer of large amounts of data between these hubs would be done by physical couriers carrying solid-state data storage devices. Improved combustion engines. With the failure of the electric grid, the internal combustion engine would remain king for transportation. The focus on innovation would be on making them as efficient and clean as possible, leading to advanced hybrids and fuel-injected engines decades ahead of our time.